Sweet.
So let's talk about intensity. Intensity is the concentration of energy in the sound beam. And it also describes the I'm sorry. It also describes the intensity. I'm sorry. The bigness of a wave.
What?
I'm just reading. Oh, you killing me. You confusing me now.
No,
I know. I'm like, what? Anyway, the concentration of energy in the sound beam. So, intensity relates to how power in a wave is distributed over an area or over space. Okay, so it depends on both the power of the beam and the area where the beam is applied.
There's a file sent to the computer if you want to let the sonar class know about our t-shirts.
Okay.
The files are so there's one that you.
It's in the email?
Yeah, Johnny sent it. So.
Sweet deal. I'll let you know. Guys, make sure you check out your emails to see. You can see what the class shirt looks like this year. Okay. You guys will be able to make your own shirt next year. But you got to collab. You and the X-ray class will make your own shirt. All right. This year, sell as many shirts as you can, so we can go to TSRT for free. But I want you guys to pay for it too. I want to go free. All right. Again, so intensity is related to the power of the beam over an area. Okay. Therefore, intensity is equal. The units for intensity are going to be watts over watts per centimeter squared. Okay. My typical values are going to be 0.01 to 300 watts centimeters squared. Okay. Just threw me for a
Where did they
moment.
get those figures from? 0.01 to 300. Where did they get
Because they're giving you the numbers for diagnostic ultrasound. So they're just testing that over a whole range of, the power of intensity of the beam through diagnostic ultrasound. I'm sure that, they're in the manufacturer in the lab kind of, determining how much power, dealing with the source or dealing with the machine itself and the transducer that is applying to the body or applying the tissue. So these are typical values based on just in the diagnostic range. But
we won't be using those ranges for anything as far as
they don't mean much. You just have to know the typical value. You just have to know that in diagnostic ultrasound, it's typically 0.01 to 300 watts per centimeter squared. Okay, so that's all I want you guys. I'm going to say it. Sis, she loves this word. I want you guys to memorize these typical values. Okay, but also important. I want you to know what the units associated with this parameter are, which is watts per centimeter squared. Okay. So again, like I said, intensity is also determined by the sound source, meaning that the manufacturer already they determine the source determine the intensity of it when they're building it with the machine and the transducer, how much that output power is going to be to the patient. Okay. So nothing we can do about that. And this is also intensity that is also adjustable when we change the acoustic power. Remember, the sound beam comes out in the shape of an hourglass, right? So within the beam, that's why the focus is so important. Within the beam, the middle of the beam is where the highest amount of intensity is. Toward the lateral wall, the lateral aspects of the beam is less intense. So intensity is the average of the power spread within the beam. Okay? Intensity is the average of the power spread within the beam. All right? Because the whole beam doesn't produce the same energy throughout the whole entire beam. The middle of the beam is a lot stronger. We'll talk about that when we get to transducers. The middle of the beam is a lot more intense than the outside of the beam. Okay? So it shoots an hourglass in a profile view, but it also comes out the shape, whatever shape of the transducer, whatever shape of the leading edge of, the face of the transducer, that's going to be also the shape of the beam, how it comes out. Okay? All right? So, again, It's determined by the sound source initially, but as sound travels and it propagates, that intensity is going to decrease. All right. So, all three of our biggest parameters, API, amplitude, power, and intensity, they all describe the magnitude, the strength, or the bigness of a sound wave. These parameters are all directly related, meaning that when one goes up, the other ones go up as well. When one goes down, the other ones go down as well. Okay? They're all directly related. So, intensity is proportional to the power. Okay? If the power doubles, the intensity doubles. All right? But intensity is also, that means it's also proportional to the amplitude squared. All right? So if the amplitude is double, intensity increases to 4 times. All right? There's our mathematical equation right there. But most importantly, guys, I want you to remember the relationship. Power and intensity are both proportional to amplitude squared. That's what it says in the book. Remember, amplitude squared. And that's how you will know the relationship between power and intensity. Okay? Our 3 biggest parameters. Remember, our 3 biggest parameters are the only set of parameters that are adjustable. Okay? We're good here, guys? We're good on our biggest parameters? Yes?
Yes.
Sweet. So, let's talk about wavelength. Wavelength simply is the length or distance of one complete cycle. Okay? What other parameter describes one complete cycle? Period also describes one complete cycle. So if I just happen to draw them on a graph and I didn't specify whether it was time or distance, look, the word wavelength tells you what the unit is going to be, right? We know it's going to be a unit of distance or length. Okay? So if I didn't, I would have to let you know that, hey, this is time or this is length, for you to know that this is the wavelength or this is the period. Okay? You would have to know those things. All right? So our units of wavelength are going to be in millimeters, meters, or any other unit of length. Okay? So just the distance. Our typical values are going to be 0.1 to 0.8 millimeters in soft tissue. Remember, we're talking about diagnostic ultrasound, and so it's in soft tissue because the way they make ultrasound machines is that they assume that they make it so the transducers and it assumes that sound is always traveling at 1540 meters per second. All right, it's always traveling through soft tissue in the body. Okay. Wavelength is the only parameter that's determined by both the sound source and the medium. Okay. Excuse me. And no, that is not adjustable. Remember, we only have 3 adjustable parameters when it comes to ultrasound. Now, those are our biggest parameters. Those are our biggest parameters. So we'll talk about, remember our layout. Remember at the very beginning of this PowerPoint, how those different parameters are laid out. And you kind of, well, I'll explain later why they're laid out in that certain manner. All right? So, as you can see, just by eyeballing this, can you guys tell me the relationship between wavelength and frequency?
The longer the wavelength, the less frequency.
I just want to hear, what's the relationship?
Or inverse.
Inversely related. They're inversely related. The lower the frequency, the longer the wavelength. That's also going to mean that that's also the longer the period, right? That's also the longer the period. Okay? So both wavelength and period are inversely related to the frequency. Okay? See, our frequency gets higher, and look how short our wavelength is. Okay? Remember, wavelength is just measured from one point on one cycle to the very same point on the next cycle. Okay? So, again, I already said this, but both wavelength and period appear to be identical, and they both describe a single cycle in the wave. All right? So just don't forget, wavelength measures the distance or the length. Period is measuring the time it takes to complete a cycle. Okay? Wavelength is measuring the length of one cycle. Okay? So I will have to give you either the lambda sign or let you know that what it is in time for you to tell me which parameter I'm looking for. I can't give you this bottom one in time and say, what's my wavelength, right? It did happen to have a time on there. I couldn't do that. You know, I would have to give you one or the other. Okay? So wavelength, distance, or
Period
length,
is in time.
and period is in time. Okay?
But they both share because they complete in one cycle.
Absolutely. Absolutely. Absolutely.
So how would you ask that question, what is the time period for this, like, what is the period for this wavelength?
I wouldn't give you wavelength and the period in the same thing because they're both related to the frequency, but they're unrelated to each other. You know what I mean?
Because one is you looking for the time.
They're both.
I do know that.
They're. I mean, let me see. How can I explain that a little differently? I wouldn't ask you to compare a relationship between wavelength and period. Okay. I would only relate that in relationship to frequency. How they're related to the frequency. Because frequency affects both of them. Okay. If you want to make that comparison, it's safe to say that wavelength and period are both directly related. If you want to have a relationship between those two, okay, because they're both related to frequency in the same manner. They're both inversely related to the frequency. Okay. So, you know, like I said, if our frequency if we have a higher frequency, we're gonna have a shorter wavelength and a shorter period. You got me? But usually I wouldn't ask you a question between wavelength and period. So, again, wavelength and frequency are inversely related. When frequency increases, wavelength decreases, and vice versa. Okay? But in soft tissue, sound with a frequency of 1 megahertz has a wavelength of 1.54 millimeters. So we can always determine our wavelength based on how many megahertz a transducer has. Okay? So, in order to get that, so for example, the book has, if we have a transducer with a frequency of 2 megahertz. So how we're going to calculate that answer? We're going to take we know our wavelengths in soft tissue are always going to be 1.54 millimeters, right? Mm-hmm. So however many megahertz it is, we're just going to divide 1.54 by the number of megahertz. Okay? So in this case, 1.54 divided, if we have a 2 megahertz transducer, equals 0.77 millimeters. That's our wavelength. Okay? And so on, you know. We get that, guys? Do it? So, I don't have my phone on me because I don't feel like doing any long division today.
So I have a question.
Yes, ma'am.
So now we have two things that are inversely related, which is frequency and period, and wavelength and frequency.
Absolutely, absolutely. Those are those relationships. Most importantly, you have to understand those relationships. Know how one affects the other. That's the most important thing of this chapter. Most important thing about physics, ultrasound physics in general, is learning how one thing affects something else. How do I adjust this? How do I fix this based on this not changing, or something like that? All right. So anybody can pull their calculator out and somebody tell me if I have a 3 megahertz transducer, what is my wavelength?
Divide by 3.
Just divide 1.54 divided by 3. Divided by 3. I think it's 0.51 if I'm on the top of my head. It's 0.51 millimeters. Is our wavelength?
0.51, yes.
Oh, that's in the head. But I can't go any higher than that. So 0.51, right? 0.51 because of course it's gonna get smaller, right? If I because they're inverse related. The higher I go up on my megahertz or my transducer frequency, the lower my wavelength is going to be, or the shorter my wavelength is going to be. Okay. So shorter wavelengths are associated with higher frequency, like we just said right here. Shorter wavelengths, high frequency. See how much more often these cycles are occurring compared to these longer wavelengths. We only have, one cycle basically from up here, okay, compared to 1, 2, 3, 4, 5, 6, 7. All right. But in diagnostic ultrasound, we do prefer. Remember, we're battling between, frequency and image quality, right? Because the higher the frequency, the better the image quality, the better the detail of an image is going to be.